talks by Anna Bušić on approximate optimality with bounded regret in dynamic matching models.
So, thank you for the invitation. And I will present let's say an effort that has been going on for a couple of years to develop a new class of queuing models that we call dynamic matching models. And the focus will be on the optimization, and this part is joint work with Sean Mine that is here. And I will give overview of previous results that have been done in collaboration with people in Europe, US, and also with Gideon from Israel. So what do we consider as dynamic matching models? If you look at the talks we had previously this week, and many of them had some matching flavor. For example, talks that are around systems that model shared economy, shared rides, or maybe ads. But also classical matching models are no longer really enough, because more and more we have stochasticity in the system, and so we have stochastic arrivals of both populations. So the idea here is to construct a bridge between matching models and classical queuing theory. As you might know, queuing theory has been a really good success story in modeling of communication networks, and matching has been really useful in economy. So bringing those two together, in idea that we might have some new theoretical tools for modeling the changes in our societal systems today. So I will first give some background on bipartite matching model and what kind of queuing systems we will consider, and then the main part of the talk will concentrate on the optimization in these systems. Okay, so just to fix the notation, if we look at the static setting of bipartite matching, then we have a bipartite graph. On one side you have demand classes and demand nodes, and on the other side you have supply, and there is some compatibility graph, matching graph, that denotes all the possible pairs we can make. And so I will denote by D of S all the classes that can be matched with a supply item of type S. And similarly for S of D. Then a configuration in this model is given by a vector x, where xi denotes the number of elements of each type. So at each node you can have several items of a given class. And then in the starting setting we have Hall marriage theorem that gives us the necessary and sufficient conditions for existence of perfect matching. Okay, and these are.
What is excited here? So what is the type of
So xi denotes the number of items of a given class I, and these are three classes of demand population, and we have also here
so each node is not one node, but
it's not just one item. It represents one class, and there might be multiple items sitting at each node. Okay. That's why also we have not just sets, but really the number of items that we need to take into account. Okay, so if you look at the systems today, then more and more often we don't have this static setting, but we have some arrivals, some arrival process, both of supply and the demand. And here is one example, living kidney donation program, where there is a patient that needs a kidney, and there is a friend or a family member that is willing to donate a kidney, but unfortunately they are not compatible. So in that case, they can sign up for into a living donor program and wait until they receive a compatible match. So okay, there are many other restrictions if we really want to consider this application, but the high-level property of this system is that we have a bipartite graph and for compatibility, and we have stochasticity both on the supply and on the demand side. So another example where we need to take into account stochastic arrivals is the example of public housing in Boston area. So this is now quite an old example, but it's a very similar story. You have families that apply for public housing, and they might specify some requirements they want. For example, they have young kids, so there needs to be a school in the neighborhood. They need a given surface to be able to live in the house, etc. And they might not want to move into certain neighborhoods because, I don't know, too far away from their work or in any case, we have a bipartite graph that can that models these compatibilities between types of houses and types of families, and then we have stochastic arrivals of both families and houses, and we need to pair them together. In that case, because of transparency of the program, and it didn't make sense to do other thing than first come first served policy, which means that a family that arrived first would get the house that that was there sitting and that they were compatible with. In many cases, actually, families wait until the available house is there. Okay, so for this specific first come first serve policy, now we have very detailed results, and this model was first studied by Caldente, Kaplan, and Weiss in 2009. They managed to describe dynamics of for simple matching graphs, such as N model, which is just two types of families, two types of houses, and then bipartite graph that is a letter N, or more in general for the graphs, bipartite graphs that are almost complete in the sense that there is only one edge missing per node. In that case, dynamics is very simple, and we only need to track how many of items are sitting there, not the whole sequence of the arrivals with their dates. Okay, that's why the system becomes much more simple, and in the general case, it's very messy because you need to track really who arrived first on both sides. So then initially they wanted to understand how many of, what is the proportion of different types of houses that are matched to different types of families. So what is the proportion of each edge under all the pairs that we observe. So then in 2012, finally this question was answered for the general bipartite graphs by using a product form solution for a slightly similar, for a similar queuing system, but that is different in the sense that only demand arrives and the supply is actually service in the system, and it's always present. So it's actually a queuing model of type call center type of queuing models. So using that, they were able to answer what are the matching rates for each edge, and then now we managed to extend these results and show reversibility of first come first served policy and product form under various state descriptions that not only allow to get these matching rates, but also the lengths of the links, which is necessary to study performance of the system, typically for the waiting time of an item until it gets matched with something and leaves the system. Okay. But this is also all about first come first served policy, and in practice this is not very easy to implement for various reasons. First of all, it's complex. You need to track, imagine that your bipartite graph is big, so you need to track all the sequence of unmatched items in the system with exact dates when they arrived in the system. So first of all, it might be a very long sequence. It might be costly to store this. But also, you might not have this information because of confidentiality reasons, because of simply it's not shared with you. Okay, so the idea is now to consider to relax this assumption that of first come first served policy, and to consider a more general demand, a more general dynamic matching models in which we will we let the question of policy open, but we have we will add a restriction that the policy can depend only on the number of items of each type currently in the system, which will be much easier to implement and for applications. So what is the model? Now at each, remember the static setting, we had a bipartite graph. Now at each node there is a queue. We assume that the arrivals happen in discrete time. So at each time there is one item that arrives on the demand side and one item that arrives on the supply side. They might not necessarily be compatible. And then according to the policy that we are going to choose, the activities that happen in the system are instantaneous matchings. Okay, is that clear? Those items that cannot be matched at a given time t will be stored in the system and will will build up in these queues here. So here, for example, if we have a blue arrival there and brown here, we see that, for example, the blue one can get matched with yellow, and this one has choice between green and red, and assume that it shows red.
So you're assuming an infinite stream of items? Do you need to keep queues bounded?
I assume that currently that at each time there is at most one arrival on each side. But in order to simplify, the presentation, what is actually needed is that over some longer period of time, the arrivals on both sides are balanced, that they're equal. If this is not satisfied, then obviously what we will obtain is a random walk on a line, in the best case,
What I don't understand is why can't you just queue everything and then match it at the end? You're assuming that if there is an available matching, you have to match, or?
Not necessarily. I open this. This is an excellent remark. We will see that an optimal policy in this case will not do that. Will not match every time there is a compatible item.
You see everything and then match it.
Because it's infinite time horizon. So yeah. So I didn't understand the. Okay. So I mean, for this application of kidney donation living donors, it made sense to assume that there is one arrival of supply and one arrival of demand at each time, because they do arrive in pairs. In the general case, you might ask also, why don't I just consider a system where they might abandon after a given time, so I don't have any restrictions on arrivals. It turns out that this is extremely difficult system to analyze. So having this restriction allows us to have some theoretical results that will give insights to good policies even in the general case. That's the idea here. Okay, so first question you might ask is, of course, if even under these assumptions of one item on each arriving on each side at each time step, is this system stable? And in the sense of whether the underlying Markov chain model is positive recurrent, and necessary condition are given by generalization of Hall-'s marriage theorem. It's actually exactly the same conditions, but with strict inequalities. And the proof uses network flow arguments in graphs. And so we managed to show that there are policies that only look into the current amount of items of each type that also have a maximal stability region, and one of these policies is max weight. And there are policies such as priority, or so max weight here corresponds to match the longest queue. If you have choice, look at the queue where there is the most item sitting and choose that one. So if you consider the opposite, which is probably the most stupid thing you can do, match the shortest queue, then this policy has a non-trivial stability region, but also some priority policies that might make sense have a non-trivial stability region. So we managed to prove that the some condition within the this maximal stability region, well, priority is not stable. That also is not trivial to show. It's experimentally you see it, but then to actually prove it, it takes some time.
For the max weight, do you always match whenever there is possible to match? Or?
Yes. Even if you do that, it's stable. So now the question is whether this is a good idea, whether we should do that or not. And as I said, if you try to optimize, for example, average criterion, this is not what you are going to do. You will have some threshold that will
So
come in.
what are you suggesting to optimize here?
Okay. So I'll answer a question in
Okay.
2 slides. So here is just to give you the form of the necessary stability conditions, and also nice side result is that it's possible to check these conditions, although there are strict inequalities, in polynomial time. So it's not always that trivial to check strict inequality conditions. Okay, you have exponential number of constraints here.
So what is mu? Mu is a distribution?
Mu is the arrival distribution. So mu, this is marginal for the demand side, and mu s is marginal for the supply side.
So
Okay.
you need to solve max weight matching. So when you're saying max weight, if you have multiple arrivals each time, you need to do the max weight matching.
So optimization. So here is the criterion for the optimization problem. We'll consider some cost function. We will assume that it's linear on buffer levels. Yes?
So just a question on the previous slide. You had an assumption that the graph is connected. Hall's theorem doesn't require an assumption about the graph being connected, so I don't really understand why you need one.
Oh, if the graph here is not connected, then it just trivially splits into 2 sub-problems. Why I need it here? Because I will require, if I have equalities, like in Hall's theorem, then I will end up with null recurrence, possibly. And so I need to avoid this situation. Yes?
And I guess I'm puzzled by the strict properness of the subset. I mean, why that's not necessary.
Oh, because of the assumption on the arrival process that at each time step there is exactly one item that comes from the demand side and from the supply side. So it's already there.
But if I had a perfect matching and I had one extra node that was not separated, I could handle anything that was n minus 1 on one side, and I couldn't handle n on the other.
But this is a stochastic thing, so if you're precisely at the threshold, it could be transient, isn't that?
Oh, but maybe it comes back to the connectedness. No, I'm just wondering that it's easy to match n minus 1 with n minus 1, but you know, if you're not testing a node, an nth node on the opposite side.
But then I will not be able to, if I'm just ignoring one node, I cannot have the condition satisfied for the, let's say I remove one supply node, I look at the other supply nodes because of the arrival rate of supply and demand being equal, it will directly not satisfy the necessary condition. But I'll just try to go through the optimization, and then we can have a longer discussion later. So we assume that we have a linear cost function on the buffer size of the buffer sizes, and we consider average cost. So Q dynamics, you have a state of, vector describing the size of Q's, Qt. Then A denotes arrivals at time t, and this is the matching activities that your policy will make. And there are some restrictions on this process ut. It has to be a linear combination of edges. So then we consider the policies that will be a function of the sum of the actual Q size and the newly arrived items. So this is denoted by X, and now we can frame this as an MDP problem for the process X, and one of the first questions that in analyzing of queuing systems that you might ask is what is the workload process? And here it's something that looks quite unusual. So how do you, okay, let me just guide you through this. Usually you define workload process as the amount of work needed to empty the system if you stop arrivals, right? So here, why this is non-trivial, if you stop arrivals and you do not have a perfect matching configuration, then nothing will ever happen. So it's actually just the new arrivals that help you empty the system. And here, and our constraints on the system dynamics are given by these inequalities in n-cond. So natural workload process is expressed in terms of these constraints. So take any subset, for example, D, and look at the difference between the items in D subset minus the items on the supply side that can get matched with this demand. Okay. So now we will, in order to have some insight on the good policy in this setting, we will consider heavy traffic consumption. Here, assume that there is one demand subset that is the most critical, so that in the sense that the difference in the arrival rate for that demand set and supply items that can be matched with them goes to 0. Okay? And once again, in our case, workload is something that is not trivial, so it can have positive and negative value. This is similar to inventory systems. So some insights will come from there. And so note that another very interesting property of these matching models is that it is very easy to avoid idleness. So in order to, because in most cases, the biggest concern is how to make sure that we can always idle. So you need some safety stocks sitting there to achieve that. And here, in order to avoid idleness, just don't do anything. Okay, so the idleness here corresponds to matching between the supply items that can serve D and D complement. So that's idleness here. So very easy to avoid. Okay, and in order to have an insight on the good policies here, we will do two types of relaxation. First relaxation is that we will concentrate only on the workload process for the critical demand set. It's symmetrical if you consider supply, so I'll just consider demand here. And then the second relaxation will be going to the continuous space. So, okay. Now, I will only consider what happens for that given workload process, and then I can just, my new dynamics becomes this. So this is arrival rate, my idleness, and then I'm left with something that has 0 mean. And then we said that we have linear cost function. if I now need to define what is my cost for this workload relaxation, and this will be noted by effective cost. And it's just a very simple linear program. And if C is linear, the solution is actually just a piecewise linear cost function. Okay, and now, the second ingredient will be going to the, now we have this one-dimensional process, so we can use results of, some ideas of inventory models similar to Clarkin's curve, and continuous approximation by reflected Brownian motion gives us actually the value of, suggests that we will need to look into threshold policy, and that the threshold, value of the threshold will be of this form. Okay, so I'm out of time, so I'll try to give you just the flavor of the main result. Under some technical assumptions here that I don't expect you to read, just to tell you that high level, this one is, the first assumption is that there was only one critical workload vector, so the others are bounded. The arrival rate for the others is bounded by something that is negative. And then there are some continuity assumption, and also there is a third assumption is that on the graph structure that we need connectivity even when we at the limit when delta goes to 0, and we need to be able to idle. There needs to be one edge between S of D and D complement. Under these conditions, it turns out that we are able, the following type of policies that we call H max weight with threshold, for obvious reasons, gives us asymptotic optimality with bounded regret. So first, what is H max weight? Well, it is max weight with a given well-chosen function H, and then on top of that we have this threshold behavior that comes from links with inventory systems. So, with the high-level idea is apply H max weight if, but if your workload is higher than the threshold, then just forbid idling. So you'd never idle until workload goes very negative, below this certain threshold that is given by the approximation by the reflected Brownian motion. Okay, so it's also interesting that, so here, this is the optimal policy. This is the, and this is the optimal average cost for the workload relaxation, but that is still stochastic. But then using the, as I already mentioned, using the continuous approximation with reflected Brownian motion, you can actually compute the value of this threshold, and then also the approximate the value of the average cost with this term that does not depend on delta. Okay, so some idea on what H is, it's a combination of two terms. One is a function of workload, and it's also obtained from this workload relaxation and links with diffusion. And then the second term induces penalty if you are deviating too much. Your actual cost is deviating from this effective cost. Okay.
So I was just trying to get some intuition behind the threshold. Excuse me. So are you suggesting that by creating this threshold, you're ensuring that matchings are big enough when you serve them? If you were serving them without the threshold, you would be serving very few edges, whereas by creating a threshold, you are creating a sort of big matching before serving.
Threshold is there to avoid cross matchings between what is capable of serving your critical subset and the rest of the demand. So it's not there to create more bigger population to perform matchings, but to avoid that you are it's in some sort creating reserves for your critical workload.
And you can automatically detect that threshold, or you need to know which is the bottleneck in order to?
That's another story. So far we assume that we know what is the bottleneck, and then if you don't know that, then you need to plug on top of that some learning mechanism to know to learn the arrival rates and then identify what is the bottleneck in your system. Okay, so here is one example of a simple NN model, and okay, we considered here that the workload vector corresponds to this node. So the workload relaxation tracks the difference of what is here and what can get matched to them. And then, so here is the cost function. And this threshold, estimation of the threshold is around 15, and then if you actually run the system with this threshold policy, you get much better results than just using max weight. Basically, these are just first results. I hope that by understanding even under these strange conditions on the arrival process and looking at the heavy traffic setting, this might give us some insight how the optimal policy might look like in the general case. So with some, I have some hope that then this can guide us to have some supervised learning that can be efficient here. So it's the important building block in understanding the general picture. And this will be very important when we go to the applications, because here we ignored many of the many other features that might come with other applications. And so there are many, many open questions. For example, what happens if you have more complex arrival processes? Will you put some? Will you just let people leave and abandon and just try to minimize this abandonment rate, or you will put into place some admission control to the system? Some maybe pricing schemes, even I think Sean would not like that. Also, there are applications that might require non-bipartite matching models. And there are some results for the stability here, but there is many other things to be done.
Does the usual sum of Q size squared turn out to be on the Asymptotic function for max weight? Or do you need some other cleverness to get to the Lyapunov function?
So for the stability, it's exactly what you think. So it's a quadratic Lyapunov function, but it's not very easy to prove it directly for the max weight policy. In order to prove the bounded drift for a quadratic Lyapunov function, you need to construct some auxiliary a randomized matching policy for which that is guided by the fluid approximation. So it comes from the network flow problems. And then once you get it for this, obviously then max weight minimizes the...
In that case, if you switched instead to using q to the alpha for some very small value of alpha as a Lyapunov function and just picked the steepest descent of that algorithm works extremely well in the generalized switch case where the serving is deterministic. I'm wondering if it would end up working extremely well here also.
Yeah, we get a threshold.
So yeah, I think that here I mean, if we are in the setting that we considered where there is a dominant set that is, I mean, critical set that you need to pay attention at, then I think the threshold is really important.
Well, then, when there's only one critical thing and you know what it is, then the problem is basically easy. The only job of the threshold, as Sid was saying, is to make sure you stay there. But when you don't know what it is, or when there may be multiple thresholds which are critical, then it's trickier. And then the weird thing is that you know the queuing system itself doesn't know which one is critical. It will have random fluctuations which push it into things which are like someone is critical, then some other things. And so the different policies seem to work. The good policies are good because they are robust to all circumstances, and all circumstances do arise just plain from random fluctuations. So I cannot believe that the threshold is absolutely vital in a formal limit of some sort, but for any system which has, when you're trying to take account of all of the fluctuations, then essentially it will see all critical regimes, and certainly work well under all critical regimes. That's my intuition from the deterministic server case. Maybe.
I don't know. I need to think about more. If you, it is interesting that in this example here, we actually didn't consider delta to be very small. It was just smaller than the others, and it was not very close to this limit, and still it performs considerably better than just max weight. So I think that this threshold can play a role even if you are not in the limit. So. Yeah, and that's a good. I mean, if I change the cost, then of course everything will change.
So that kind of goes to my own biases with reversible things. But you've got this nice work that sort of looks into reversibility of these systems. Then you go into this dynamic bipartite matching model. And I was wondering if are there reversible dynamics there? But I mean, the issue essentially with max weight, if there's any form of feedback in the system, it's going to lose its stability properties. So max weight has issues that it's not single hop, it loses stability, whereas if it's reversible, then you don't get that anymore. So you've got a patient, you treat them, they need to come back for a second period of treatment. Max weight's going to be unstable.
So I take as a message that as long as single hop, I'm fine. But if I'm going into multi-hop systems, then it might be worth to consider even storing more information, but having stability. It's yeah.
Performance, or even better performance in a lot of situations than max weight backpressure. So then if you can preserve the reversibility properties from the first part to the second.
So what is interesting here that I don't have the plots for this case, but first come first served was very similar to max waiting for this particular example. Now we don't include multi-hop systems, so that might be the case, but it was performing slightly better in general, but it still had very large queue sizes.
I think we're eating into our break a lot, so maybe we can.
Yeah, there are technical issues. I think we can maybe.
Break left at this point.
So if you have any suggestions of applications, just let me know. That might give some ideas of what variants of the model it's worth to consider. So.
Say that if you start with the initial condition, which is not the end,